The difference quotient. So you had some function, right? You had some function that's traveling around, right? And you wanted to know what's the instantaneous rate of change right there at the point x comma f of x, right? What did you do? Well, you took a point and then you just brought it closer, and all the while you were calculating the slope of the secant line, right? So what did you do? You were trying to find this slope, right? And how were you calculating that slope? You're doing the limit as h goes to 0 of what? It was f of x plus h minus f of x divided by h, right? You were bringing those 2 points closer together, right? The key thing to look at here, and this is what kind of keyed me off to, I think, truly understanding what's going on here, is you have h right here and you have h right here, correct? So what are you effectively doing? You are bringing, here's this secant line, right? What's that point right there? Well, if this right here is h, right? You're going over h, okay? So what's that point right there? That's x plus h, comma, f of x plus h, right? So actually this denominator is really, if you wanted to write it out, what is it? It's x plus h minus x on the denominator right there. That's why it just comes to be x. Everybody with me so far? So the idea here, that's h, and that's f of x plus h. Okay, so here's what's going on in 3 dimensions, and I'll do my best to sketch this right here. Okay, so there is some surface, right? Correct? And you are sitting here, and you want to know if, and I'm going to go down to the xy plane here. So that's the xy plane below that surface. You see the blue right there? So that's the xy plane below that surface. Are you okay with the picture I'm drawing right there? When you're talking about a direction, you're talking about going in any one of these directions, right? Let's say that could be north, that could be south, that could be east, that could be west, right? But the point is your direction is written as, if you're trying to find the directional derivative on a three-dimensional surface, your direction is written in how many dimensions? 2 dimensions, right? Right? Everybody, so what did we do? We said, okay, so we have a function f of xy and we're going in some direction u, right? And what did we say u was? We said u was a unit vector, right? Well, let's just say, and we did it as what? u1 plus u2 is u2i, this to j. You with me so far? So the direction we are going, so let's just look at the direction we're going in. Here's the xy plane, everybody. Everybody, surface is flat. We're looking at the xy plane right here. And let's say we were going in this direction. Let's call that the u direction right there. So we'll call this part u1 and this part u2. The orientation is off. Don't worry about the orientation, but that's how we broke up the direction, right? So floating above it, here's the point we're trying to find the directional derivative of, right? So we're floating in space above it, right? And it's saying, like, there's a surface that's bubbling, and you want to walk in this direction. If this was your shadow going straight down. Is everybody with me so far? I haven't done anything new. This is what a directional derivative means. Imagine there's a surface right here, and we're at this point, and I say go in that direction. What is the steepness going to be? That's what we're doing. Are you with me so far? Okay, so here's the thing. So there's going to be some sort of like 3-dimensional path right there, and we want to know, like, what's the tangent line right there, right? That's above this. Everybody with me so far? What's this right here? What's that distance right there? If that's u1, not u prime.
u1 squared plus u2 squared.
Yes, so what is that? u1 squared plus what?
u2 squared.
u2 squared, right? So here's the thing. If it's a unit, hold on, exactly. So if this is a unit vector, the square root of u1 squared plus u2 squared is what?
1.
Is 1, right? So when you're doing this tangent line here, over here, we just had 2 dimensions, right? Imagine this now, it can be turned, right? It can be turned in 3 space, right? This, we're doing the same thing, but we're taking a slice either here or here or here or here or here or here. It could be any direction we want to go in, right? So here's the challenge. The challenge now is this vector right here. How did we make this smaller? What we do is we keep on calculating. We want to know what the tangent line is right here. So what did we do? You calculate that secant line, the next secant line. You bring this point closer, right? So what did we say? We put h's in front of these, right? Mm-hmm. And we let h go to what?
0.
We let h go to 0. We let h go to 0. So the point is, every time, so again, here's that point. I'll draw this a little closer. Here's this point, and there's some, this is the slice of the surface that's over this direction. Everybody sees what I'm doing here? I'm cutting a slice over that, from that direction. So you have this mountain, and I say go that direction, so I cut it, and I'm looking at it from the side here. What do? You have this point right here. What is that point? That point right there is a comma b comma f of ab, right? And then what happens here? You go over to here and you go up, correct? And here's the new point, right? This distance right here, do you see this? The base of that triangle, what is the distance on the base of that triangle? H times what? The square root of u1 plus u2 squared, right?
Yes.
Correct? And then what did we do here? Well, A is an x direction, right? So what is this new point? That new point is A plus u1, B plus what? u2, right? And then what's the next one? F of A plus u1, comma, B plus u2, right? The point is you've moved over and up to get to that new point. So as this point travels, so we're trying to find what's this slope. We're still trying to come up with a scalar, a single number, right? It's this number over this number, and then it's this number over this number, and then it's this number over this number, right? You have to scale this by the same amount you're scaling everything else. You have to scale this by the same amount you're scaling this. This point, this height of this point, changes as you change u1 and u2. And if it's a unit vector, what does this become? 1, right? So if it's not a unit vector, so let's say it wasn't a unit vector, what was that formula you had? You had going in the u direction, f of xy, what was it? You did it a bunch last night, what was it? What was that formula?
Oh, it's
Grad f dot what? Dot u, right? So what's the only thing? What happens if I changed it to this? F in just some arbitrary direction. It's going to be grad f dot what? V over the magnitude of v. That's it. So here's the thing. If v is a unit vector, what does that become? 1. It is the same formula. The idea is, so basically it comes down to this. If I had to do it in one sentence, if you don't have a unit vector, you have to divide by the magnitude of the directional vector, because the amount for the difference quotient, as you take that limit, you have to scale down the horizontal distance the same amount the relative same amount you scale down the vertical distance, right? And if the horizontal distance is now h times the square root of u1 plus u2. Does that kind of make sense right there? Does that kind of make sense? So over here, it didn't really matter. As h went to 0, you had the same thing in both the top and the bottom. You had h up there and you had h down there. It was the same thing, right? But over here, where's the picture? Over here, if you take that slice, this distance right here is h times that magnitude, right? So that has to scale down. You're not just scaling down h, you're scaling down that whole magnitude. Has to be proportional to the vertical change. Basically, if you don't remember anything I just said, just remember that. Okay? That's about it. What was the shortest way you could notarize that? It was just that f.u, right? Mathematicians, when they write the same thing over and over again, they just eliminate everything.
How do you say that? Is it just grad f?
I think it's just grad f. I think you just say grad f. And I think that's the del sign, I think. But I think grad f.u. That's it. That's totally it. Hey, there it is. Exciting. Super exciting. Super exciting. Okay, so you did a ton of these, and I think you did, we also talked about this. So let's go up here. Oh, we just talked about this, right? What is the geometric definition of dot product? What is the geometric definition of dot product? It's this one right here, correct? The dot product of two vectors is the magnitude of the two vectors multiplied together times the cosine of the angle between them, correct? Well, what is u? U is defined as we're defining it as so it has to be 1. So you end up with this equaling grad, the magnitude of the gradient times cosine of theta. Theta is the angle between the two, right? So let's look at the circle here for a second here. How would you maximize this? Well, what's the biggest thing cosine theta can be?
1.
What's the smallest thing it can be?
0.
Well, it could be negative 1, right?
Negative.
Cosine of theta equals 1 when what? When theta is equal to? 0, right? Hey, if the angle between two things is 0, what does that mean those two vectors are? They're going in the same direction. They're parallel, right? So this tells us that to make this as big as possible, because the magnitude of the gradient stays the same. If you pick a point, there's only one gradient. That's what I mean. If you have a point and a function, there's one gradient. The gradient of a function at a point stays the same. But the direction you go in for the directional derivative changes. So how would you make this maximized? What direction would you go in? The same direction as the? No, so you're choosing u. You're choosing u. The gradient is fixed. The gradient's going like this, and you can go in any directional derivative you want. How would you maximize this right here? You would go in which direction? The same direction as the? So the gradient points in the direction of maximum rate of change. The gradient points in the direction of maximum rate of change. Now, similarly, how would you minimize this? What's the smallest you could make this in terms of non-negative? How do you make that small? Well, what's the smallest thing cosine can be and not be negative? 0, and that's when theta is equal to 90 degrees, right? So what does this mean? If u goes in the same direction as the gradient, you will have a maximum directional derivative. But if you are perpendicular to it, it will be 0. Think about it this way. When you're on the side of a mountain driving a car, the road usually isn't straight. If you want a flat road, has anybody been on Interstate 1 before? Pacific Coast Highway in California? It's on the side of the ocean. It's really nice. You can see the Pacific Ocean. You're traveling along, and generally speaking, roads want to be flat, generally speaking, right? It's a lot of work to go up and down, so flat roads. But is the road straight? No, the road does this, right? So what is it actually doing at every given point? It's actually being perpendicular to the gradient, which points in the direction of staying the same height. Staying the same height, staying the same height. Now, if you're on a flat surface, everything else becomes kind of arbitrary, but that topological map, what could you tell me? What's one feature? What could you tell me is going on right here? What's going on right there?
Increasing steepness.
Yeah, let's just assume they're going up. Let's say this was height of 5, 10, 15, 20, 25. So what could you say about if you walked up, let's say this is path A, and let's say this right here is path B. Let's call that path A and path B. What could you tell me about path A and path B in terms of steepness? In terms of steepness. A is steeper than B. Do you agree with that?
Yeah.
Right there? Okay, so here's the thing. If I gave you this topological map, could you theoretically, if you had some clay, like map out, like create this for me? Could you like model it out? Sure, it's kind of cool. I did that in 7th grade. It takes a long time. Yeah, okay, so let's say you were sitting at this point right here. Let's say you were standing at that point right there. What did I tell you the gradient? What direction does the gradient point in? The gradient points in the direction of maximum steepness, right? So what direction at that point is the gradient pointed in? It's kind of like this, right? Let's say then when I get to here, what direction is it pointed in? Oh, it's pointed in the same direction, right? So let's say I change this topology a little bit. It's always going to point in the steepest direction. So in this case, it kind of looks like this, right? What's the steepest direction? What's the steepest direction from this point right here? Kind of like this maybe, right there?
So it's going to point to the
steepest path.
The highest value.
So at this instant, at that instant, at that instant, and I'm just going between them, right? That's almost a straight line. Does it have to be? No, it doesn't. I could draw a topological map that looks like this. I could say like there, 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 there. So if I was here, if I wanted to pick the steepest direction, how would I pick the steepest direction? What do I do to pick the steepest direction? I go in the direction that gets me to the next contour line. Exactly. So it'd be going to like here, right? And then what direction do I go in? Here, right? And then what's the shortest distance here? Kind of looks like maybe here, like this. And then what's the shortest distance here? Like maybe there?
Yeah.
And then maybe, I don't know, something like that. So that path would be if you had to classify that path, that would be the what path? The steepest path, right? Here's the thing. Every time you take a step, does your gradient change? Yes. So theoretically, you have to change your sampling, right? So this would be at each contour. So you're going to get questions that are going to be like, sketch the steepest path, or like sketch all the gradients. Does that kind of make sense? What direction do you, let's say this is point A, what direction do you have to go in to stay at the same altitude? If you're at point A, and that's the gradient right there, what direction do you have to go in?
Yeah.
Along the contour at that instant, right? Which is in relation to the gradient will be what to the gradient? Perpendicular. So either you're going to go like this or you're going to go like that. There's two different directions you could go in, right? So if you wanted to keep on calculating that, you walk a step and then calculate the gradient again and then go perpendicular to it, and you'd stay at the same altitude the entire time. You'd stay at the same altitude. Yeah, so the magnitude of the gradient vector grad f is the maximum rate of change of f at that point. Large when the contours are close together and small when they are far apart. Because if they're far apart, that means it's more flat than if they are closer to